Hello everyone, I'm Amir Hakim and I'm a student in Education College. Today, I'm going to talk about capacitance and its application in real-life situation. So, what is a capacitor? Capacitor is a device that has the ability to store and release energy in an electrical and electronic circuit. Well, unlike battery, capacitor doesn't store chemical energy. Instead, it stores energy in the form of an electric field between two metal plates. But how exactly do we charge a capacitor? Well, let's break through it down step by step. But first, let's take a look on the inside of the capacitor.
Alright, as you can see, this is a capacitor that can be easily found in the lab. Now, let's take a look inside of it. Well, as you can see, there is two pieces of conducting material like metal that are separated from each other. This piece of paper or insulator known as dielectric is put in between these metal plates to make sure that the two metal plates don't touch each other. Now, let's see how these plates could be used for. Well, when the two metal plates connected to a battery, the electrons flow from the negative terminal of the battery towards the left side plate, making it negatively charged. Then, positive terminal of the battery attract electrons from the right plate, making the right plate is positively charged. The capacitor will store the charge from the battery, and the charge that's stored in the capacitor is now called as capacitance.
The capacitance is the amount of charge that a capacitor can store per unit potential difference that apply across it. The formula can be defined as C equals to Q over V, where C is a capacitance and its SI unit is in farad. Q is a charge and its SI unit is in coulomb. And V is a voltage or potential difference and its SI unit is in volt. The amount of capacitance depends on these three factors. 1. The area of the plates. 2. The distance between plates. And 3. The nature of the insulator between plates. Now, let's go through these factors step by step.
First of all, let's take a look on the area of the plates. When the area of the plates are large, the accumulated charge are able to distribute themselves over the area. This makes the amount of charge that can be stored on the plate based on the potential difference from the power supply increase as the plate area increase. Imagine this. Think of each plate of capacitor as a hole, where the electric charge that moving into the capacitor are a people. If the hole is small, only a few people can fit inside it comfortably. That means it can only store less charge inside of it. But if the hole is larger, more people can gather inside it without crowding, so it can hold more charge inside of it. This shows that the capacitance is directly proportional to the area of the plates. Next, let's talk about the distance between the plates. When the potential difference in the battery is constant to its terminals, the electric field between plates increase as the distance between plates decrease. The closer the plate separation, more charge can be stored in the capacitor. This shows that capacitance is inversely proportional to the distance between plates. From these factors, the formula of capacitance can also be defined as C equals to epsilon naught multiplied with A over D, where C is a capacitance in farad, A is the area of the plates in meter square, D is the distance between the plates in meters, and epsilon is the constant permittivity of dielectric between plates.
Furthermore, capacitors can be connected in two types of circuits. One is in parallel circuit and 2 in the series circuits. So let's discover it one by one.
When the capacitors are connected in a parallel circuit, the potential difference across the capacitors is same and equal to the potential difference in the circuit. Next, the total charge for the capacitor that connected in parallel circuit is equal to the sum of the charge of each capacitor in the circuit. Lastly, the equivalent capacitance for capacitors in parallel circuit is equal to the sum of the capacitance for each capacitors in the circuit. When the capacitors are connected in a series circuit, The total potential difference across capacitors is equal to the sum of potential difference for each capacitance. Next, the charge on capacitors that connected in series are the same in every capacitors. Lastly, the inverse of the equivalent capacitance of capacitor in a series circuit is equal to the sum of the inverse of each capacitance. In comparison, we can see that the equivalent capacitance for capacitors that connected in parallel circuit increase. Meanwhile, the equivalent capacitance for capacitors that connected in series circuit decrease. This shows that capacitors that connected in parallel circuit has higher equivalent capacitance than the capacitors that connected in series circuit.
Now, let's discover the potential energy in capacitance.
When a capacitor is charged, it stores electrical energy in the electric field between its plates. This energy comes from the work done by the battery to move charges into the capacitor. Initially, no work need to be done by the battery to bring the first charge inside the uncharged capacitor, since there is no electric field between the plates opposed the flow of the electrons. But after that, work need to be done to bring more charge into it. This is because electrons from the inside of the plate will repel the incoming electrons since they have the same negative charge. As for that, the work must be done by the battery to overcome the repulsion of the electrons that already inside of the capacitor.
From this situation, we can define that the energy stored with a symbol of U inside the capacitor is equal to the half of the charge Q multiplied with voltage V. The energy stored in the capacitor can also be defined as U equals to the half of capacitance multiplied with voltage squared.
In a discharged capacitor, the potential difference across the capacitor begins at zero as no charge stored inside of it. From this graph, we can define the energy stored inside the capacitor by using the area under the graph. Since the area under the graph is in triangle shape, we can define that energy stored is equal to half of the base multiplied with height, where the base is the charge inside the capacitor and height is the potential difference inside the capacitor. Well, if you take a look, this is where the energy stored formula comes from.
When the capacitor is discharged, the energy in the capacitor transfer and convert into the other form of energy.
For instance, if capacitor connected to a light bulb, the electrons flow from the discharged capacitor pass through the filament inside the bulb. These electrons collide with atoms in the filament and transfer kinetic energy in the bulb. The electrical energy from the discharged capacitor is converted into the terminal energy cause the filament to generate heat and into radiant energy to produce a light.
So now let's talk about dielectric. So dielectric is an insulating material that placed between the plates of a capacitor, just like you've seen in the previous video. The purpose of adding dielectric is to increase the capacitance by allowing plates to be placed much closer without touching, which also decreases the separation between the plates. It also can allow more voltage to be applied onto the capacitor by preventing it from breakdown. The strength of the material to become the dielectric can be defined by the value of dielectric strength. The purpose of dielectric strength value is to describe the maximum field that a material of dielectric can experience without breaking down. The new value of capacitance with dielectric can be defined by multiplying the factor of K, we also known as the dielectric constant, with the value of capacitance without dielectric, which we label as C naught. New voltage with a dielectric can be defined by dividing voltage without dielectric, which we label as V naught, with a factor of K. The dielectric materials increase the ability of the space between the plates to store charge. The new permittivity of the material can be defined by multiplying the factor of K with permittivity of the material without dielectric, which we define as epsilon naught. Next, the energy density of a capacitor. We can replace the epsilon in the energy density formula with the new permittivity formula, which turns to U equals to half of the factor K multiplied with epsilon naught and E squared. We can define new charge is equal to the factor K multiplied with a charge without dielectric, which we label as Q naught. The new electric field with a dielectric can be defined by divide the electric field without dielectric, which we label as E0, with constant K.
It's fun facts time. Did you know that capacitors play a main role in electrical distribution? Well, capacitors help the power systems work more efficiently and maintaining the quality of power supply. Firstly, it helps in power factor correction. Most loads like motors are inductive and cause the current to lag behind the voltage. This creates reactive power, which does not do useful works but still loads the system. Capacitors supply leading reactive power, which cancels out the lagging reactive power from inductive loads. Next, capacitors help maintain stable voltage level across the distribution network. In long distribution lines, voltage drops out occur due to load demand. When capacitor bank is switched on, it injects reactive power into the line. This reactive power compensates for the voltage drop caused by the line impedance. This helps maintain the desired voltage profile, preventing equipment malfunctions and ensuring consistent power equality for consumers.
Alright, that's all for today. Thanks for watching. I hope you learned something new from this video, and thank you and goodbye.